Okay, the next thing we're going to work on is the cross product. It's also known as the vector product. It's very important when you're thinking about these two different types of vector products. They both take in two vectors, but you have to remember the dot product, symbolized with the little dot, is the one that gives you a number, out, or an angle depending on how you do it. This is the cross product. The cross product still takes those two vectors, but it's going to give you a vector out. Okay? So what we're going to do is we're going to start by just kind of going through a couple of examples. So we're going to start here with A cross B. So I've already written out the vectors A and B, and what we're going to do is we're just going to do the cross product of these guys. So if we write these as a matrix, which if you remember these from linear algebra, hopefully you'll be in good shape here. All we have to do is we have to say, okay, well, I need determinants, but I'm going to first evaluate this coefficient, right? So you've got 1 times, well, these aren't going to be evaluated when you're evaluating this coefficient, so we just get 1. And that's our x component. And then we're going to evaluate our other component here. So then this one and this one won't be evaluated, so we'll get 1, which is the coefficient, times 2. Okay? So then that leaves us with 1 times 1, which is just 1, and then comma, 1 times 2 is 2. Okay? So that's going to be the dot product for just a quick little 2 by 2 or a two-dimensional vector. But I think the dot product is more interesting once you start working with 3 dimensions. So I'm just going to define a couple quick 3-dimensional vectors. So we're going to have, let's do P. It's going to be 1, comma 2, comma negative 1. Okay, and then Q will take to be 3, comma 1, comma negative 2. And we're going to cross those two. So we're going to cross P and Q. So what we're going to get here, I'm going to write this just a little differently than I did on that last one to kind of illustrate how this looks on a bigger scale, a 3 by 3 scale. So what we can do on 3 by 3 that's really nice is we can actually write our old school friends from physics, I, J, and K. And those just tell us which component these are. If you don't like those, you can use X, Y, and Z. Totally fine. Whatever you like. Okay, so then we're going to write our first one. So the beginning of the cross has to go first. So you have 1, 2, and negative 1. Okay, and then this next one is 3, and then 1, and then negative 2. Keep in mind with the dot product, the order matters a lot. If you do this order backwards, you will not get an answer you are expecting. We'll try and touch on that here in a little bit. With the dot product, you should still get the correct answer even if you do them out of order. That is not the case with the cross product. And that's because we're taking determinants. So I'm going to zoom in a little bit so we can kind of talk about how this is going to work. So when we take a determinant of a 3 by 3 matrix, I have a whole video on this, so I'm not going to spend a lot of time on it. We're going to evaluate this term. So then we're not going to worry about the column or the row that term's in, and then we're going to make our little fishy here with an eyeball so we can do our multiplication. So we're going to get I hat is multiplied by this determinant here. So you get 2 and negative 2, and then the minus, the eyeball is telling you to remember to put a minus here in between them. Okay, and then you have negative 1 times 1. Okay, and then we're going to do the same thing, but for the other components. So we've got to do J now, and like I said, I'm not going to spend a ton of time explaining how all this works, but there are coefficients in front, which I guess I'll write that real quick. So this is negative 1 to the m plus n power, which is your row and your column. So in this case, it's 1 plus 1, so that's even, so that's all positive. Whereas here, you have negative 1 to the, we're still in the first row, but we're in the second column, so now it's odd, so it's going to stay. And so then you have j hat in our parentheses, so we can do our multiplication. And so then we've got 1 times negative 2, so that's just negative 2. And then again, remember your minus, so you've got minus, and then negative 1 times 3. Okay, and then finally we're going to have our negative 1 to the 4th power, which is going to be 0. And then you've got k hat. It's not 0, sorry, but it's just going to be positive 1. So k hat, And then here, we're not evaluating the k row or the ijk column, so we've got 1 times 1 minus 2 times 3. So we got 1 times 1 minus 2 times 3. Again, I'm not going super slow through the determinants because I have a whole video just on those. Feel free to watch that if you're a little confused on how those work. Now we're just going to go through and do our quick algebra skills to make all this make sense. So we've got negative 4 here minus negative, so that's going to be plus. So we've got negative 4 plus 1, so negative 3 I hat. Keep this negative in your mind so you can write it out front if it helps. You've got negative 2 here, minus negative 1 times 3, so this is negative 3, but then that's negative times negative, so it's positive 3 with the negative 2 is positive 1, but now it's a negative 1, so we're just going to write negative j hat. And now out here we've got our k hat, positive, and then we've got 1 times 1 is 1, minus 2 times 3 is 6, so that's going to be negative 5 in here. So instead of that, we're going to write minus 5k hat. And that is our vector that corresponds to the output of P cross Q. The other way you could write this is in our other vector notation where you just have negative 3, negative 1, and negative 5. Now let's look at that compared to the vectors we put in real quick. So I'm going to copy them and pull them over so we can compare them all at the same time. Okay, so if we look at these, we can say, okay, well this one kind of looks like it's just these two multiplied and flipped, but this one's not these two multiplied and flipped, and this one's not either, so that's not what's going on. So what the cross product actually tells us is it gives us a vector that is normal to our other two vectors. Now if you don't remember what that means from your physics class, that's totally fine, but a normal vector is going to be something that is going to be 90 degrees in every component from every part of the vector. So in 2 dimensions, what we kind of get here, or I guess not in 2 dimensions, but with 2 vectors, if we had them both just on a regular xy plane like this, this is the plane. So we kind of have our 3-dimensional thing going on here. I did not draw it great, I'm sorry. Should have done it all at once. Yeah, I'm actually going to just delete that and try again. Okay, so let's try this again with our 3-dimensional. Good enough. Okay, so in our 3-dimensional plane, let's say we have some vector here and some other vector over here. Whoa, that was weird. Okay, so when I take the cross product, I'm expecting some vector that's going to come kind of this way, actually. So we're looking for something maybe over here, depending on our perspective, and that should be the cross product of those two. So you've got, if you remember from physics, you have your right-hand rule. So you have, 2 vectors here, which are your index finger and your middle finger, and then you put them in the direction that you need them to be in, and then your thumb becomes the orthogonal vector. So to find that, you do your cross product, right? You cross this guy, and you get this guy. Same thing going on here. This is actually the math behind that. Okay. I don't know what else to really mention about the cross product other than it uses sine in the full expanded formula, but I don't think I've had a context where I've needed the full expanded formula, so I don't think it's worth going over right now. If it comes up and enough people ask for it, I'll make a separate video for that. But it's based on sine, the other one's based on cosine. So there's 2 implications of that. So if we have cosine as part of our formula for the dot product, which I'll squeeze back over to find that real quick. So we have cosine in our dot product. Well, there's an angle value where cosine is equal to 0, which that angle value, I think as we all know, is going to be 90 degrees. So if we get a 90-degree angle here, all of this stuff on the right goes to 0, so our dot product equals 0, which is kind of the long way around to say if you take the dot product of 2 vectors and you get 0, you know that they're at a right angle to each other, those 2 vectors. Now, if we go back to our cross product down here, we just talked about how this one's sine. So we know sine has a property at 0 degrees where it's 0. So if you take a cross product of two vectors and you get 0, that means they're actually parallel. Okay, and so I'll just write that down really quick. So if you get A cross B equals 0, comma, A and B are parallel. Okay, and then if you get A dot B equals 0. Man, my tablet does not like the bottom of the screen. Okay, A dot B equals 0, then A and B are perpendicular. If they're in 2D, it's perpendicular. If they're in 3D, you call it orthogonal. So, kind of as a recap, you can take the cross product of A cross B and get an orthogonal vector, but if you get 0, you've actually found out that your vectors are parallel. There is no orthogonal vector. Whereas if you take the dot product of two vectors, you're normally going to get the angle between them. But if you get 0, you've actually found out that they are orthogonal, right? And if they're parallel, you get 1. Okay, I think that's all I want to go over for the cross product.